All right, so this week we are looking at the precursor to our earthquake module, and then leading into all of our other geomorphic hazards, because all of them deal with plate movement, and plate tectonics and continental drift are really what get the discussion going. And so we look at earthquakes and tsunami and volcanic eruptions and even landslides to a certain extent that can be caused by the idea that our plates move. If you remember from your reading, we have Alfred Wegener, who is not the first, but certainly the most recognized for coming up with this idea that the continents have moved from when we've seen them in the past. And we talked specifically about Pangea, but there were certainly other supercontinents or continents where we have more continents put together than we do today, that we can look at and see some of this evidence. And so we're going to look at this idea of plate movement in detail and our types of plate boundaries that we have. So how are the plates actually moving? What did our plates once look like? How did they move to get where they are now? Our first type of plate boundary is our divergent plate boundary. Okay, this is where we have two plates pulling apart. We call this tensional stress. What you are going to find throughout the course of the semester is I like to give you different ways to remember what's going on here, and sometimes they're a little kooky, but sometimes the kookier, the more easily you are able to recall them when it comes to things like tests and homework assignments. So if we're looking at divergent plate boundaries, we have tensional stress. There's a couple of ways that you can look at this, some a little more off the wall than others. The first is, if you think about anything that you put tension on, you're pulling in two different directions. So as we have our plates moving apart, they're moving in opposite directions, then there's tension between our plates as they pull apart. Another thing I like to think about, and this is one of those little kookier ways to think about it, is if you have tension with another person, typically you avoid them. So if you want to think about like walking in the other direction when you see them coming down the hall because there's tension, whatever you're going to use to help remember is what's important to you. So, link on to whatever example kind of brings it back for you, so that you can remember that when we have divergent plate boundaries, we have tensional stress, because as we move through these slides, we're going to talk about when we have plates converging, what type of stress we have. So you're going to want to know what the plates are doing. Are they moving to each other or away from each other or past each other, and what type of stress is associated? So again, divergent tensional stress. Okay. What we have here in this screenshot here on the right is we basically have this nice illustration that's showing you that as we pull our plates apart, we're basically creating this space that magma from underneath the crust is now able to make its way to the surface. Now, we do not see this on land very frequently, but we see it very clearly when we look at oceanic crust, and specifically our best example is the mid-Atlantic ridge, where we have basically North America and South America pulling away from Europe and Africa as we spread down the center. Okay, as we pull these plates apart, basically what happens is our crust thins out, and as it thins out, it allows that hot magma to rise into that space and then eventually melt that rock and create new rock then there to be exposed. We do see this in Iceland. Iceland is being pulled apart because it sits over the mid-Atlantic ridge, but we see a majority of this happening on the ocean floor, and then because the ocean's on top, it's a little bit more difficult to see, but just think, as you pull apart, it weakens. One way to think about this is like if you try to chew gum and then blow a bubble, right? So you thin it out kind of by putting your tongue through it and then being able to blow air into it more easily. And then obviously that gum thins even more as it stretches and puts air in it. Okay. We have this occurring in several places around the globe. When we look at a plate tectonic map, which you have seen in your text, you will notice that you have arrows pointing in opposite directions. That's giving you a key that we have a divergent plate boundary. When we are looking at this on a small scale and in a faulting scale, we are looking at what's a normal fault. Okay, so basically, you can think of this idea, it's normal to have tension. Again, whatever you want to use. But what you should notice is, if you think about putting two blocks together, if you pull them apart, okay? If you have your hands on both of them, they're not going to move anywhere. But let's say we have them held up by two pieces on the outside, and we slowly just release the tension, or release the pressure. I don't want to say tension because tension is pulling apart. If we release the pressure on them, we'll see something similar to the left, where basically one block falls lower than the other. And sometimes you can see this in like brick walls or in archways where they've pulled apart, and so they've actually slid downward. And so in this case on the left, we're looking at our hanging wall moving down and our foot wall staying kind of where it is. If we look at the image on the right and where we can see this kind of happen in the real world outside of cartoon world, what you'll notice is if we look at the striations on the rocks, so we have some dark and some light, notice that on the left, we can see those striations move downward. So if we were trying to make a straight line coming across from the left, we would kind of hit that top one, and we would actually have to take a step up to continue on the other side. If you look very carefully, basically right between those two red arrows, you can actually see where that plane is, or the fault scarp is, where that slippage is occurring. Our second type of plate boundary is when we have converging plates. Now, you'll remember from your reading, we can have two continental plates running into each other, we can have two oceanic plates running into each other, and we can have one of each, one continental and one oceanic plate. And we'll talk more specifically what can happen with those. But right now, we're just looking at what happens when plates are trying to get to the same spot, basically. With converging plate boundaries, we have compressional stress. Okay, so you can think CC, converging compressional. You can think that when you try to make something smaller, so basically take something and put it into a smaller space, you compress it. You can think of our plates wanting to be in that same spot, so they're kind of running into each other and compressing. Again, however you want to think about it, it's just important. Our picture here on the right, which comes from an animation, basically what you're looking at there is you can see the folding in the rock, just like when you crush a can, right? The aluminum, and especially if you're really good at it, some people I've noticed are much better than others, you can compress it down until it's like almost an inch thick, right? It's all folded in on top of itself, almost like a slinky. So when you push that slinky together, it all kind of folds up together on itself. Okay, so we can see this with rock, and a lot of times when we have two continental plates running into each other, we get what's called mountain building, because basically they compress, or you can think of like a car accident with cars that have non-plastic bumpers but have the metal bumpers, because plastic bumpers just break, but metal bumpers were a little more sturdy, and so they kind of crumple in on top of each other, and so we get this folding, and a lot of times that folding creates height, and so we get these taller mountain features based on this compression. So if we look at the Appalachian Mountains, those were actually formed because we had compression of Africa before we were in Pangea running into the North American plate, and it kind of basically folded up, North America then kind of folded up on top of itself and created those Appalachian Mountains for us. Okay. When we're looking at faults, so again on the smaller scale, we're looking at reverse faults. So we have two plates moving into each other, okay? Again, we're moving in reverse direction here. But again, we have that compressional stress. Now, if you think about putting your hands together and kind of, and I would be doing this in person with you if we were in class, and pushing, notice how one pops up, one hand will eventually kind of like pop up over the other, okay? And so we see that with our reverse faults. And notice again our image on the right. It's a little clearer. If you look right between the two red arrows, you can see that our fault plane there, but notice there's kind of a textural difference. It's a little bit of a color difference, but it's more of a textural difference here, where we have that sandy color on top, and that kind of it's a little more gray, but it looks smoother, and then we go back to that sandy. Notice that if we're this time we start on the right hand side of the picture, if we move to the left towards that fault plane, we have to step down so that that block on the right hand side was pushed up and over the block on the left hand side. Another type of boundary we have is our transform or strike slip. And in your text, they do talk about the difference between transform and strike slip, and transform being a specific type of strike slip boundary, sorry. But really what we're looking at here is we have two plates that are trying to slide past each other. Okay, so it's just like walking down the hall with someone when it's really crowded, you're just trying to get past them. And as we know, when we walk in crowded situations, we get our shoulders caught, and so we might have that little bit of a jerking. And so when we talk about earthquakes next week, think about how basically we have these rough edges of these plates, and even if they're just trying to slide past, not get to the spot where the other one is, they can get caught, and then when they jostle loose, then we can get that earthquake activity. Okay, this type of stress is called shear stress. There's shear on it, if you want to think of it that way. I like to think of scissors. So typically, and I don't know if it's a generational thing or if it's just a sewing thing, but like a lot of times sewing scissors, fancy sewing scissors that are very expensive, are called shears. Okay, and when you think of how a scissor works, right, the two blades slide past each other. Okay, so we have shear stress here as they're trying to slide past one another. Okay, most prominent strike slip boundary in the United States is going to be the San Andreas Fault. Okay, so we have basically the North American plate and the Pacific plate moving past one another. Where California currently sits is a very small portion of it. Mostly Baja and very small parts of the coast of Southern California sit on the opposite plate or over the opposite plate at this point, so they're moving in two different directions. But we do see a lot of movement there and potential for earthquakes. And if you were paying attention this summer, you'll know we had some activity as well. Okay, again, looking on the smaller scale. So strike slip fault again, we're looking at shear stress, again, sliding past one another. What we're able to look at though is if you look at your image on the left, we can determine whether the plate has moved to the right or to the left. So do we have a right lateral or left lateral movement? Okay, if we look at our image on the left, so our cartoon blocks again, and this time we're looking at the one that's marked right lateral, notice that if we walk down that road into the screen, when we get to the fault plane, we have to step to the right to continue on the road. Okay, if we move to the picture on the left, the image on the right labeled left lateral, notice if we walk into the screen on that road, we step to the left. The same directional change happens if you flip it around and you pretend like you're walking out of your screen. Okay, if we now move to the big image on the right where we can see our agricultural rows, if we either follow a green line of plant, if you can see the little plants that are there, or kind of the raised part of the row that's a little bit lighter in color. If we walk into our screen, notice that when we get to that fault plane, we'd have to step to the right. So that would be an example of right lateral movement. When we have these linear features, it's a lot easier to tell which direction things are moving. So, review. Divergent plate boundary, tensional stress. Converging plate boundary, compressional stress. Strike slip, shear stress. If you like letters, strike slip, shear, SS. Converging, compressional, CC. Divergent, you just have to remember then it's tensional because it doesn't actually match. But this will become important because as we look into our text, you'll have some maps. We'll see what's going on globally at every different plate boundary. The other thing that's important to remember as we start talking about earthquakes is it's not uncommon that if we have one plate move or shift, that it's not going to push some of the other plates and potentially push them to the stress release point, meaning it puts enough added stress on it now that it's going to shift another plate, and then we can see an earthquake occur. So stay tuned for next week because this definitely becomes important as we start talking about earthquakes.